Hi everyone. In this video, we are going to look at Euler diagram. What is the Euler diagram and how to use Euler diagrams to determine if a given argument is a valid one or not. So let's get started. What is a Euler diagram? Basically, it consists of a rectangle and which represents the universal set, also two circles to represent two sets, two individual sets. Usually when we draw a Euler diagram, we don't draw that rectangle. If you look at your homework, you don't see those rectangles. And the most important part when you draw Euler diagram is about how to represent the relations between two sets. If we have two sets, there are only four possible relations. So let's focus on how to represent these four relations using two circles. So each side is a circle, like I use A and B to represent those two sides. So we have circle A and circle B. So try to focus on these four relations, which I call them four models, because this is a foundation for you to create Euler diagrams and to answer all of the argument questions. So let's look at these four relations one by one. First, all A are B. That means every element in A is also in B. In terms of the two circles, those two circles, the circle A will be entirely inside the circle B. That's how we represent this relation. So if I draw it, this is my circle A. You can also call it set A. So, and let me label that. And B will be outside, entirely include circle A inside it. So as a result, if you have an element in A, it will be automatically in B, right? Because the entire A circle is in B. So this is how we represent all A are B. And the second relation, sum A are B. Whenever you have this sum at the beginning of this description, you will have two circles that are partially overlapped. So that's how we represent them. So this is our A circle, and this is our B circle. They're talking about that part of A that is also B. So they're talking about this part of A. Because this part belongs to A, also belongs to B, right? Sum A are B. Sum A are B. Sum in logic means at least one. At least one. So that means there's at least one A. That means at least one element in A that is in B. So sum A are B. So that's the second relation between A and B. It's two circles or two sides. Now third one, sum A are not B. So still we start with sum. We're going to draw the two circles the same way here. This is our B, this is our A. But this time they are talking about those elements that are in A that doesn't that's those elements A but not in B. So they are talking about this part of A. This part of A, elements in this part of A that are not in B. Some A are not B. So that's another relation. The last one, no A are B. So no elements in A that are in B. So there's no overlap. So we draw the two circles totally separated. So this is A, this is B. As long as you have element in A, it's guaranteed it's not in B. No A are B. These are the four relations. I call them four models again. That's all you need to answer all of those argument questions in your homework. Okay, Now let's do a exercise problem. Just get familiar with these four models. I pulled this out from your homework assignment. So let's look at it. First of all, this red circle is not really a circle, the shape, but let's call them circles. Okay. This red circle represents all of those people who live in Chicago. And this blue one represents all of those people who like windy days. Now, A, B, C, D are the four options when you do that multiple choice problems. I do those multiple choice problems. This is a drop-down list. That's how you answer your homework question, actually. After you determine which one is your answer, you just click this arrow and click on one of these letters to select your answer. Now, let's look at this one by one. So I'm giving this diagram. I need to determine which statement in here describe this scenario. Okay. Apparently, according to our model, we see this blue circle is entirely inside the red circle. That is our model called OARB. OARB. And this is our A, this is our B. And this blue circle representing those people who like windy days. And this red one represents those people who live in Chicago. So basically, it goes like this. If I don't even need to look at this description, just try to translate this diagram into English. So it goes like this. All those people who like windy days live in Chicago. Then I look at which one say the same thing. So I notice that the first one says, everyone that likes windy days lives in Chicago. This is exact same meaning. So for this one, we choose A. You just click letter A in this drop-down list. So now let's look at the second one. So very much the same kind of problem. We just switched between blue circle and the red one, right? So all those live in Chicago like windy days. Something like that. Started with O because this model is OARB, but this time A is the red circle. People live in Chicago, right? Everyone living in Chicago likes windy days. So that's the meaning of this diagram. So we choose B as the answer for the second one. Now let's look at the third one, which is on the next slides. One by one again. So this one, apparently, these two circles are totally separated. We have model for that. We call it no A or B, right? It doesn't matter which one is A, which one is B. So now people living in Chicago likes windy days. Now people who likes windy days live in Chicago. Either way, depending on what is given. So apparently it has to start with no. So no one living in Chicago likes windy days. So this is our answer. Oh, this is D. Excuse me. That's D. Right? The last one. So we have two circles that are partially overlapped. This is the model some A are B or some A not B. So either way, you have this overlap region. That means your statement should start with some. And this is the only one C that start with some. Some people living in Chicago like windy days. They refer to this part of the red circle because red circle represents all of those people who live in Chicago. But this portion of those people living in Chicago also inside the blue circle, that means like windy days. So some people living in Chicago like windy days. That's exactly this description. So the answer is C. See, this is how you read these diagrams, Euler diagrams. Now let's look at how we use Euler diagram to determine the validity of an argument. So how to do that? This is a general process. First, in order to determine whether a given argument is valid or not, you have to draw a Euler diagram to represent those premises. And then based on your diagram, you want to determine if there's if there are other conclusions other than the one that is given. if there are more than one conclusion that can derive from your representation, from your Euler diagram, that means the argument is invalid one, because a valid argument can only have one conclusion, no matter who draw that conclusion, it will be the same. So the last part here says if the premises are insufficient to determine the location of an element or a set mentioned in the conclusion, then the argument is invalid. Sure, it is invalid. If you don't even have enough information in those premises to determine argument, you don't even have a conclusion. And how do you say it's valid or invalid? There's no way to determine, so it's invalid because you cannot even draw a conclusion. And this number 3 says the argument is valid if the diagram cannot be drawn to make the conclusion false. That means everybody will draw the same conclusion. Otherwise, if you could draw a different conclusion, that means original conclusion is false, because a valid argument will have unique conclusion. Your conclusion will be the same as the given one if it is valid. Okay, let's look at examples. When you see these examples, study all of these examples, you have much clear picture about how to represent those premises and how to determine whether the given conclusion is a valid one or not. Okay, the first one. The key is being able to represent these premises correctly. That's your foundation, because you're going to draw your own conclusion based on your Euler diagram. Now, look at this one by one. Keep in mind, all you need to do all of this is those 4 models. Always think about those 4 models. First one, all people who arrive late cannot perform. So each of these premises will be represented by 2 circles. So think about those models. We start with all, has to be all A or B. What is A? People who arrive late. People who arrive late. This is our circle A. People who cannot perform. This is our circle B. So A has to be entirely in B. So this is how I represent that. Let's make things a little bit simpler. This represents people who arrive late. Okay, this whole thing, so that I don't have to write every single word. Let me get some markers here. So B has to be bigger. I mean, enclose this A. So people who cannot perform will be our second circle B in our model. So this green one represents people who cannot perform. So this way I represent the first premise. Now second one, all people who cannot perform, which means there are green circle, those people inside green circle, are ineligible for scholarships. This is a new circle. All A or B model again start with all. So our B here represent those people who are ineligible for scholarship. It has to be this green circle has to be entirely inside this new circle that I'm going to draw. I'm going to use a red color. Notice that there's only one way to draw this green circle. To draw this new red circle. This red circle has to enclose this entire green circle. There's this only way to draw it. The reason I emphasize there's only one way to draw this red circle in this case is that if there are more than one way to draw it, you have to look at this conclusion first before you draw the second premise. Later on, we see those kind of examples. But for now, this is how we represent these 2 premises. There's no other way to represent it. So now, after we represented you never try to represent this conclusion. Okay. After you represent this premises, look at what circles are involved in your conclusion, in the given conclusion. All people who arrive late, which is blue one, are ineligible for scholarships. That's a red one. So this conclusion involves this blue circle and red one. Then after you identify which two circles are involved in the conclusion, you want to state the relation between this same two circles using your own diagram, using your own Euler diagram. Since this blue circle is entirely inside the red one, that's our model OARB, right? This means all those people who arrive late are not eligible or are ineligible for scholarships. Now look at what they say. All people who arrive late are ineligible for scholarships. So we get the same conclusion. So this is a valid one because valid one only has one conclusion, no matter who represents the premise. So this is the valid one. We draw the same conclusion. Okay, next one. All poets appreciate language. OARB model again. That's all poets. And green circle to represent those who appreciate language. Now look at the second one. All writers appreciate language. Now pay attention, we have a little bit more complex situation here. We have a new circle that represents those writers. Since we have this model OARB, this green circle represent appreciate language, those people, right? So this new circle, the red circle, going to be entirely inside the green circle, OARB. Now here we have a potential issue here. As long as I draw this red circle within this green circle, I'm good in terms of representing the second premise, right? But we have a blue circle inside the green one. If we don't have this blue circle, there's no issue. I can draw in any location I want to draw that red circle. There's no difference. But since we have this green and we have this blue circle, potentially I could draw different scenarios. Since I have more than one way to draw this red circle, I need to look at the conclusion first. Why? Because I need to go against the conclusion. If I draw different conclusion, which means this is invalid. Again, valid argument can only have one conclusion. If I draw a different conclusion based on the Euler diagram, that indicate we have invalid argument. That's why we want to go against the conclusion, the original conclusion. This is also the reason we don't want to represent the original conclusion, because our goal is not represented, is to test if this is unique or not. That's why we want to go against it. So let's say which two circles are involved in the original conclusion. Poise, which is the blue one, are writers. Writers is the red one that I'm going to draw, OARB. Their conclusion is that poise circle will be entirely inside that red circle that I'm going to draw. I'm going to go against that. This is my writer circle. So I am still good in terms of representing the premises. All writers appreciate language, the OARB, I'm still right. But according to my drawing, in terms of this poets and writer relation, I say some poets are writers, and they say all poets are writers. Apparently, we have different conclusions. So this is invalid one. And you don't have to draw this red circle this way. You can draw the red circle entirely inside the blue one, or entirely outside the blue one, as long as you provide a counterexample that go against this relation, you are good. You don't have to draw all of those scenarios, because in order to make some statement false, you just need to provide one single counterexample. For me, I just draw it this way. I could draw it here, entirely outside the blue circle, but still within green one, still makes this false, right? I can draw this red circle entirely inside the blue circle so that all writers are poised. That also makes this false. Either case is okay, as long as you present a different scenario, which will give you a different conclusion. That will make this invalid, because again, a valid argument can only have one conclusion. Now move on to the next slide. All mathematicians are logical. All A are B. So this is a mathematician circle. Let's just use the math and represent that. Our B circle is those people who are logical. So this is logical people. No points are logical. That's our model called no A or B. So A, B have to be totally separated, right? So we have a new circle that's poised, and this logical circle, which is green one. That means between the red circle I'm going to draw and this green one, they cannot have any overlap. They have to be totally separated. And there's only one way to draw that. That means we draw this red circle outside the green one. There's no other way to draw it, so that this time we don't need to look at the conclusion, what circle involving conclusion in order to draw this red one. We don't need to look at that, because there's only one way to draw this red one. That's out, which is outside the green circle. So this one represent points. Now, since we have our Euler diagram completed, now let's look at which two circles are involved in the conclusion, because I want to go against it. They say no points. This red circle are mathematicians. So they are talking about relation between blue one and the red one. Since these two are totally separated, we say no points are mathematicians or no mathematicians are points. Either way, what they have no points that are mathematicians. So we have same conclusion. So this is the valid one. That's the only conclusion between these two circles we can draw. No points are mathematicians. So this is the valid one. Next example. All freshmen live on campus. So that's the OA or B model. Freshmen. Green circle represents those who live on campus. Now look at the second premise. No people who live on campus can own car. So live on campus, we have this circle already. This is no A or B model, or A is people who live on campus, which is green one. And this B is those people who can own cars. Okay, with this new circle, it's going to be red one. So no A or B, this or A. So the red circle has to be drawn outside this green circle, because green circle is all A in here. No A or B. This is representing people who can own cars. Now, this is the only way to draw this second premise, so that I didn't look at this conclusion first. Now, what two circles are involved in the conclusion? Freshman and red circle own car, right? To say No freshman can own car. No A or B. They are totally separated, which is correct. So this is a valid conclusion, valid argument. Valid argument. We don't say valid conclusion, but valid argument. Next one. All mathematicians are logical, just like the previous one, but this problem is different. These mathematicians are logical. These logical people. No points is new circle. No points are mathematician. That means we want this new red circle to be separated from this blue circle. Now here's the thing. We will have different scenarios. Since we only need to draw this red circle outside the blue one to fulfill the requirement of the second premise, I could draw it here, which is entirely inside green circle, or I can draw it here, which partially interact or overlap with green circle, or entirely outside the green circle. See, I have different scenarios. Whenever you have different scenarios, you look at the conclusion first to see which two circles are involved in conclusion, because you want to go against them again. So they say no points, which is the new circle, red one, are logical. This is logical. So they want this red circle to be entirely separated from the green one. That means it has to be outside in order for this to be correct. But I want to go against that. I can draw this partially overlapped with green circle so that it's not entirely outside. I can even draw it inside green circle. As long as I don't touch this blue one, I'm good for the second premise. So either way is okay. So I just draw it this way. This is my points circle. Now the conclusion is between the red one and the green one. For my drawing, I say some points are logical. Some points are logical. These points, this is logical. Some points are logical. They say no points are logical. We get different conclusions. This is invalid argument. Now, next one. All people are mortal, so all A are B. So by this point, everybody is familiar with this general procedure, right? This people circle. This green one represent all those that are mortal. And second, some mortals are students. So we have new models, some A or B, right? So this new circle, red circle represents student. They want this mortal circle partially overlap because this is some A or B, right? Partially overlap with green with the red circle. But here's the thing. I can draw it this way so that they are partially overlap. I can draw it this way to also encounter the blue circle to partially overlap with green circle. In other words, I have more than one way to draw the second premise. That's why I need to look at the conclusion first before I draw the second premise. I want to go against the conclusion if that is possible. So which two circles are involved? Some people, so the blue circle involved, students are involved, red circle. They want this blue circle partially overlap with red circle, some A or B. Now I want to go against that, but at the same time, I have to have this red circle partially overlap with this green one. So now this way I fulfill the requirement of second premise. This is our student circle. But for my drawing, no people are students. They say some people are students. We got different conclusion. So this is invalid argument. Let's say next one, we have two more examples. All mathematicians are logical. By the way, this is not the same as the previous one. Looks, the first part is the same. This mathematician and logical people. And second one, some points are logical. So we want to draw this red circle so that it will partially overlap with the green circle, right? But there are different scenarios. I can draw it this way without touching the blue circle. I can also draw it this way, which will overlap with the blue circle. As soon as you realize there are more than one way to draw the second premise, you want to look at the conclusion first. So which two circles involved? The point circle, that's our red one, mathematicians. So they want this red circle partially overlap with the blue one. So I'm not going to do that. So these are points. So from my drawing, you can see some points are logical, still satisfy the requirement of the second premise, right? Some points are logical, but for my drawing, at the same time, no points are mathematicians. They say some points are mathematicians. So we have different conclusions. This is invalid. Invalid. And the last one, this video. All children love to swim. So OARB model. These are our children circle. Love to swim. Those people who love to swim. The green one. Now, Michael Phelps, this is an individual person. Now, Michael Phelps is a very famous person. He was a say Olympic champion, and he won a lot of golden medals. But it doesn't matter for us. It's just an individual. So we use either a cross or a dot in your Euler diagram to represent an individual item or individual person. Okay, you don't use a circle to do that. So Michael Phelps loves to swim. So I need to put this dot or cross. Either I'm going to use cross inside the green circle. Anywhere is fine to fulfill the requirement of the second premise, right? But we have another circle inside the green one. If I put Michael Phelps here, what is here, that will make difference depending on what the conclusion is. It will make difference because we create different scenarios. So now let's look at what these have here. Since we have different scenarios, I want to look at the conclusion first. Michael Phelps is a child. That means their conclusion is that Michael Phelps is inside the blue circle. Guess what? I need to go against that if possible. So I put this cross here. So Michael Phelps loves to swim. Still good. But according to my drawing, Michael Phelps is not a child. So I have different conclusion. This is invalid. I hope you, after this example, you understand this whole process. Actually, it's not that hard as long as you know this process, you know how to represent those premises. And that's all for this video. See you in the next one.